Hello. In this lesson, we're going to learn about something called diagonalization of a matrix. It sounds like a very long and complicated term, but the idea is basically that we want to rewrite a matrix. We kind of want to factor a matrix in a certain form. And so our goal is, given some 2 by 2 matrix, call it capital A, perhaps with entries A, B, C, D, we'd like to rewrite it in the form, I kind of think of this as factoring. Form A equals the product of 3 matrices, P times D times P inverse, where D is going to be what we call a diagonal matrix because it's only going to have 2 numbers on it. I'll call those numbers lambda and maybe the Greek letter kappa, and zeros elsewhere. So this is sometimes called a diagonal matrix. And the matrix P, this will have some numbers in it. I'll call them V1, V2, W1, W2, where these numbers, you might notice the Greek letter lambda. Oftentimes, people use that letter when calculating eigenvalues and eigenvectors of a matrix. And sure enough, that's where these numbers in the matrices D and P will come from, where the numbers lambda and kappa are eigenvalues. And these 2 vectors that would form the columns of the matrix P. And so if I thought of that as partitioned into 2 column vectors, and I'll call those vectors V and W, those are eigenvectors of the matrix A. It's very amazing that this even works, and we'll explain why this works in a moment. One question you might be asking yourself is, why? Why would we want to diagonalize a matrix? There's a few reasons. One possible reason would be to calculate powers of a matrix. And so, for example, here's one application. Calculating powers of a matrix. Say A to some number n. Right? If you want to multiply together, like let's say A is maybe the matrix 2, 3, 4, 1. If you want to calculate A squared, it's not too bad, right? We'll take 2, 3, 4, 1 times 2, 3, 4, 1. If it helps, we can always partition this into rows and columns. And remember, we're calculating a bunch of dot products when we calculate matrix product. See, the top left entry is going to be 4 plus 12. That's 4 plus 12 is 16. And the top right entry is going to be 6 plus 3, that's 9. The bottom left entry is going to be 8 plus 4, that's 12. And the bottom right entry is going to be 12 plus 1, that's 13. And squaring a matrix isn't too bad. Let's say we want to calculate the third power. Well, if you have the second power, that's not too bad. We can think of A cubed as A squared times A. So I would take what we previously calculated, 16, 9, 12, and 13, and then multiply that again by the matrix A, 2, 3, 4, 1. Right, we can do this. Let's see, I've got 16 times 2, that's 32, plus 9 times 4, that's 36. Next entry is 16 times 3, that's 48, plus 9 times 1 is 9. Bottom left entry, 12 times 2 is 24, plus 13 times 4, that's 52. Bottom right entry, 12 times 3 is 36, plus 13 times 1, that's 13. And if we add these together, we'll get 68. See, 48 plus 9 is 57. 24 plus 52 is 76. 36 plus 13 is 49. Right? Straightforward, maybe a little bit tedious. But imagine if someone asked you to calculate a to the 10th. This is perhaps something you don't want to do. But if you have a diagonalization of your matrix A available, it's not too bad. Let me show you why. And so let's use factorization. A equals P times D times P inverse. And so imagine if we wanted to calculate A squared. And so instead of multiplying A by itself directly, we combine these matrices, P, D, P inverse, P, let's see, right over there, P, D, P inverse. At first, it might seem like this is an incredibly bad deal. Instead of multiplying one matrix times itself, you're going to multiply 6 matrices. But it turns out some of these cancel. We have P inverse times P. Right? When you multiply a matrix times its inverse, you get the identity matrix, which effectively cancels out. And what you're left with is P times D, will give you D squared, times P inverse. And there's something special about the matrix D. It's something called a diagonal matrix. Now recall that if D has this form, lambda 0, 0k, if you want to calculate D squared, things work out extremely nice. Mostly because of all those zeros, but in particular because of their placement. And so if we calculate this product, we're going to get, see, lambda squared in the top left, top right, got lambda times 0 plus 0 times kappa, that's 0. Bottom left, 0 times lambda plus kappa times 0, it's another 0, and a kappa squared. And squaring a diagonal matrix isn't too bad. And in fact, if you do any power of a diagonal matrix, and if we did D cubed, we take D squared times D. Again, the math works out very nicely. You're going to find that you get lambda cubed, 0, 0, and kappa cubed. And similarly, so again, not too bad calculating the square of D. So still, A squared, it's still easier to calculate A squared than it would be to calculate P times D squared times P inverse, because P inverse might be a little bit difficult to calculate. Well, not too bad for a 2 by 2 matrix, but still you're doing more matrix multiplications here. What if we were to calculate A cubed? Right? And again, using this factored form, this diagonalization, P times D times P inverse, P times D times P inverse, P times D times P inverse. Again, we're going to get a lot of nice cancellation here. Right? The P inverse and the P cancel out. In fact, they cancel out twice. So it's not too bad. And then you're left with a bunch of adjacent D's. You've got a D here, a D here, a D here. So this simplifies to P times D cubed times P inverse. As we saw before, D cubed is not too bad to calculate. Because it's a diagonal matrix, D cubed, you can figure that out just by cubing the elements on the diagonal. And so A cubed, these are about the same amount of effort to calculate. And you might notice the pattern here. If you were to calculate something like A to the 10th, I'm not actually going to write this out 10 times, even though it would be fun to cancel all of those factors out. For similar reasons, this is going to be p times d to the 10th times p inverse. And d to the 10th, as you may have guessed from following this pattern on calculating powers of the matrix D, right, this is going to be p times lambda to the 10th, 0, 0, kappa to the 10th, times p inverse. Right, so on the left-hand side, calculating the 10th power of a matrix directly, this requires 9 matrix multiplications, right? Multiply A and then by itself 9 more times. Over on the right, you've only got 2 matrix multiplications. Right? So in general, life is a lot easier. To calculate the nth power of a matrix A, you could write that as P times D to the nth power times P inverse. So if you can diagonalize a matrix, if it has enough eigenvalues and eigenvectors, then it's much nicer to calculate a power of a matrix this way. But first, we really have to understand why this is true. Why, or when, can we write A is equal to P D P inverse, where, as you may recall, D is a diagonal matrix, lambda 0, 0 kappa. P is the matrix, we'll call it columns V1, V2, W1, W2. And lambda, kappa are eigenvalues, and the vectors V, containing V1 and V2, and the vector W, the second column of P, containing W1 and W2, are eigenvectors. Well, why can we write this? Why does this work out? Well, let's go ahead and do some calculations here. So going on to the next page. Okay, let's assume that we have 2 eigenvalues and eigenvectors. So let's assume that A times that vector V is equal to lambda times the vector V, and also A times that vector W is equal to kappa times the vector W. And so in other words, on the left-hand side, remember A is the matrix, I'll write it as little a, b, c, d. Right, this first equation, once we multiply this out, on the left-hand side we have A V1 plus B V2, and the second entry would be CV1 plus DV2. It's equal to lambda V1, lambda V2. If we expanded, that's what we would get. Similarly, the second equation results in AW1 plus BW2. It's a top entry. CW1 plus DW2 is a bottom entry. Is equal to kappa W1, kappa W2. Right, so we're assuming that lambda and kappa are eigenvalues, V and W are eigenvectors. That means these two equations are true. So then we will let P be the matrix containing V1, V2, W1, W2. What happens when we multiply A times P? What happens if we multiply the matrix A, B, C, D times the matrix V1, W1, V2, W2? When we multiply these two matrices together, let's see, the top left entry is going to be A V1 plus B V2. The bottom left entry will be C V1 plus D V2. Then on the top right, we'll have A W1 plus B W2. Bottom right will be C W1 plus D W2. Boy, those numbers sure look familiar. That's because we saw them in our assumption. Because of our assumption, right, we can replace them with these values. A times P is the same thing as lambda V1 and lambda V2 for the first column, kappa W1 and kappa W2 on the second column. All right, so that's what A times P looks like. What do we get when we say D is the diagonal matrix, lambda 0, 0 kappa? What happens when we multiply P times D? And again, P is the matrix whose columns are eigenvectors. So V1, V2, W1, W2 times this matrix, lambda 0, 0 kappa. Because of all those zeros, actually works out pretty nicely. You'll see that what we get, see the top left entry, is going to be lambda times V1. The bottom left entry will be lambda times V2. The top right entry will be, let's see, 0 plus k times lambda 1. Sorry, k kappa times W1. Then the bottom right entry will be kappa times W2. And hey, will you look at that? Those two things are the same. Since those two things are equal, we know that AP is equal to PD. If we multiply both sides by P inverse here, we get A times P inverse is equal to P times D times P inverse. A times P inverse, well, the P and the P inverse cancel out. And really, this is just equal to A on the left-hand side. And that's where our diagonalization comes from. Right, so therefore we know we've verified by algebra that A can be written in this form. Again, assuming that P, sometimes I'll think of that as the eigenvector matrix. Like the eigenvectors are columns. And D, I like to think of that as the eigenvalue matrix. These aren't official terms at all, but they're a nice way to think about the concepts here. All right, so enough theory. Let's actually do some calculations here. Let's do some examples. In all the examples, we have basically the same goal. We're going to calculate the diagonalization of a matrix. And we'll find the diagonalization of a matrix A, and then we'll use it to maybe calculate a power of the matrix A. So use it to calculate maybe A cubed and A to the n. Right, we can actually get a nice formula for the nth power of a matrix. And so this is what all the examples will look like. Now let's start off with a matrix, and I'm going to pick all these examples so the corresponding polynomial is relatively nice. For this first matrix, let's say 1, -2, 1, and 4. Hopefully you recall from a previous video that the eigenvalues and eigenvectors, in order to calculate these, we have to start off by calculating the determinant of A minus lambda times I. And so we want the determinant of the matrix 1 minus lambda, negative 2, 1, and 4 minus lambda. We're going to set that equal to 0 when we're done. If this is equal to 1 minus lambda times 4 minus lambda minus 1 times negative 2. We'll expand this out. We'll get 4 minus 4 lambda minus lambda plus lambda squared minus negative 2. That'll be plus 2. So this is lambda squared minus 5 lambda plus 6. Right, and we want the determinant to be 0 for this matrix. This will give us non-trivial solutions to the eigenvector-eigenvalue equation. This happens to factor nicely. This becomes lambda minus 2 and lambda minus 3 equals 0. So the two eigenvalues that we get here, I'll just call the first one lambda, and the second one, to be consistent with what we've done before, kappa, that'll be 3. And those are the two solutions to this equation. Right, so we're partially there. Once we have the eigenvalues, the next step is to find the eigenvectors. Let's go ahead, turn to the next page. So this far, we have A is equal to, just to recall, 1, negative 2, 1, and 4. And we found out that lambda equals 2 and kappa equals 3 are the eigenvalues. Next, we want to find the eigenvectors. Right, so remember that we have the equation, for instance, for the first one, A times some vector V equals lambda times some vector V. We can rewrite that as A minus lambda times I times a vector V equals the 0 vector. So sure enough, that's exactly what we're going to write. And I'll take the first case, where lambda equals 2. Matrix A minus lambda I turns into 1 minus 2, minus 2, 1, and 4 minus 2, times some vector V, V1, V2, equals the 0 vector. If I turn this into a system of equations, let's see, this first row is negative 1 and negative 2. So negative V1 minus 2V2 equals 0. The second row is 1 and 2. So that dot product with V1, V2 becomes V1 plus 2V2 equals 0. And sure enough, as is often the case, is always the case when you're coming up with an eigenvector, you're going to notice some redundancy in these equations. Turns out the first equation is negative 1 times the second equation. So we have a free variable here. We can pick one of these variables to be whatever we want. So maybe we'll pick, to keep the math simple, maybe pick V2 equals 1. And then we'll solve the other equation for not V2. We picked that value. We'll solve for V1. V1 has to be negative 2 to get these equations to work out. There are lots of possible eigenvectors, but it's a good idea to pick the simplest one we can. So we'll get this first eigenvector to be negative 2, 1. And that will be the first column of our eigenvector matrix P. Now also, remember there's 2 eigenvalues, 2 eigenvectors. And so now we're going to try to solve this equation. A times vector W equals kappa times vector W. And same equation as before, just switching up the variable names a little bit. And the case here is kappa equals 3. So we'll take the matrix A and we'll subtract the eigenvalue from the correct places. We have 1 minus 3, negative 2, 1, and 4 minus 3 times W1, W2 is equal to the 0 vector. So we're going to go ahead and turn this into a system of equations. And so we'll have negative 2W1 minus 2W2 equals 0. Then the bottom equation will be W1 plus W2 equals 0, expanding that out. And as usual, a sign that we're on the right path here. The first and second equations are redundant. The first equation is negative 2 times the second equation. So that's good. We'll pick some nice simple values here. Maybe W1 equals 1, W2 equals negative 1. And that gives us our next eigenvector. That's the eigenvector associated with kappa. W is 1, negative 1. All right, let's go ahead and transfer this information onto the next page. And so A, you might recall, was the matrix 1, negative 2, 1, 4. We have some eigenvalues and eigenvectors. Lambda equals 2 and kappa equals 3. And associated to each one of these, we have an eigenvector. Call them V and W. And remind ourselves of what they were. V was negative 2, 1, and W was 1, negative 1. Negative 2, 1, and 1, negative 1. And if you were so inclined, you could check. Right, as we have before, that A times V equals lambda times V, and A times W equals kappa times W. Right, you could check that they satisfy the eigenvector, eigenvalue equations. But what we'd really like to do here, right now we're interested in diagonalization of a matrix, where we're going to create the eigenvector and eigenvalue matrices. So P is the matrix whose columns are the eigenvectors. So negative 2, 1, and 1, negative 1. It's going to be the matrix P. The matrix D, our diagonal eigenvalue matrix, is 2, 0, 0, 3. And last but not least, we need P inverse. Right, so we're going to use our inverse formula applied to the matrix P. And so first, 1 divided by the determinant. So negative 2 times negative 1 is 2, minus 1 is 1. That's my kind of fraction. And then, see, we're going to swap around the numbers on the main diagonal. So negative 1 and negative 2. And we'll negate the numbers on the off diagonal. So negative 1, negative 1. And so there's our inverse matrix. Negative 1, negative 1, negative 1, and negative 2. And as usual, I'm a big fan of checking. We could check. So we don't have to check. But if you're feeling so inclined, we could check to make sure we calculated the inverse correctly by multiplying P times P inverse. Make sure you get the identity matrix, 1, 0, 0, 1. All right, so if we want to calculate A cubed, for example, right, by what we said earlier, we can calculate that as P times D cubed times P inverse. So we have the matrix P, which is -2, 1, 1, -1. Then I'm going to calculate d cubed. Now this only works for diagonal matrices. I can just cube the numbers on the diagonal. 2 cubed is 8. 0, 0. 3 cubed is 27. And then p inverse is -1, -1, -1, and -2. All right, and I'm just going to multiply these together 2 at a time. And so I'll start with these first two. See what we get. So I'll get -16. Top right entry, get 27. The bottom left entry will get 8. And the bottom right entry will get -27. It's not so bad. We'll carry down this other matrix, -1, -1, -1, and -2. And so now we'll multiply together these two. I'll put my helpful lines here. Let's see, this first dot product is going to be, write out the sum, -16 minus 27. Then the top right will be 16 minus 54. Bottom left will be -8 plus 27. And bottom right will be -8 plus 54. We can work those out. Let's see, -16 minus 27 will be -11. 16 minus 54 . 16 minus 54, -38. Minus 8 plus 27, that should be 19. Minus 8 plus 54, that should be 46. All right. And again, that's about equivalent to calculating a cubed, right, without having to do all this extra work. It still works out to be about the same number of matrix multiplications. But hopefully you'll see that, if you needed to calculate an even bigger power, like a to the 10th power, it'll be much easier to use a formula like this. And again, to show us how nice this generalizes, we could get a general formula for a to the n for this particular matrix. So let's go ahead and do that. And so let's say we want a formula for a to the n. Well, since a can be written as p times d times p inverse, a to the n, we know that can be p d to the n p inverse. All right, so let's actually just work out what that's going to be. A to the n is going to be equal to, in this particular example, I know d to the n is 2 to the n, 0, 0, 3 to the n. I'll put p inverse in here. Need to remind myself of what these were. Going back a page, let's see, -2, 1, 1, -1. -2, 1, 1, -1. This other matrix I remember was -1, -1, -1, -2. Okay, so now a formula for a to the n. First, I'll go ahead and multiply these first two matrices. Let's see, I'm going to get -2 times 2 to the n. So I can actually simplify that. I could write that as -2 to the n plus 1. See, the top right entry is going to be 0 plus 3 to the n. The bottom left entry is going to be 2 to the n. The bottom right entry will be -3 to the n times, I'm going to carry down this matrix on the right, -1, -1, -1, and -2. Multiply together those two. let's see, I'll have a top left entry is 2 to the n plus 1, those negatives cancel, minus 3 to the n. Top right entry will be 2 to the n plus 1 minus 2 times 3 to the n. Bottom left entry will be negative 2 to the n plus 3 to the n. Bottom right entry will be negative 2 to the n plus 2 times 3 to the n. There we go. And with that formula, calculating a to any power is as straightforward as it could be. All right, let's do maybe one more example together. I'll switch colors just for fun. Let's see, for this example, let's say A is the matrix, I don't know, let's say negative 4, 1, 7, and 2. And again, we'd like to go ahead and find the diagonalization. Right, so we want to be able to write A as P times D times P inverse. And once again, these numbers have been chosen ahead of time so that there is a diagonalization. Right? We'll get a nice polynomial that can be factored. If you had some polynomial which couldn't be factored, or you couldn't find the eigenvectors, then this wouldn't work out. But in all these examples, things are going to be fine. Right? The first step, which you may recall, is finding the determinant of A minus lambda times I. And so the determinant of minus 4 minus lambda, 1, 7, 2 minus lambda. That's going to be minus 4 minus lambda times 2 minus lambda minus 7 times 1. We're going to set that equal to 0 at the end. Go ahead and expand this, negative 8 minus 2 lambda plus 4 lambda plus lambda squared minus 7. This works out to be lambda squared. See, these two combine to give us plus 2 lambda. Constants combine to give us minus 15. All right, we want to set that equal to 0. Let's see. This should factor nicely, I think. This is going to factor as lambda plus 5 and lambda minus 3. All right, so we get 2 eigenvalues. We'll maybe call lambda 3, and the other one, to keep things clear, I'll call that kappa, make that negative 5. All right, the next step is to find the eigenvectors. So we'll do that on the next page. So recalling that A was the matrix negative 4, 1, 7, and 2. And we know that lambda equals 2 is an eigenvector. It's like, no, not lambda equals 2. Lambda is equal to 3, right? Yes. Confusing this with the previous problem. Lambda equals 3. So we have A minus lambda I times some vector v is equal to the 0 vector. Let's go ahead and calculate that out. So A minus lambda I is minus 4 minus 3, 0, 7, and 2 minus 3. Wait, why did I put a 0 up there? That should be a 1. Right, this times v1, v2 should equal the 0 vector. Let's turn this into a system of equations. We'll have negative 7 times v1 plus v2 equals 0. And for the second row, we'll have 7 times v1 minus v2 equals 0. We have that redundancy in our equations, which indicates we're on the right track. We've got a free variable we can pick. So let's say choose v1 equal to 1. And that forces v2 to be equal to 7. That will be our first eigenvector, 1, 7. Let's do the other case. We have kappa equals -5 as our other vector. So setting up a similar equation, a minus kappa times I times vector w equals the 0 vector. In this case, subtracting a -5 is adding 5 to the diagonal entries. So -4 plus 5, 1, 7, 2 plus 5 times w1 and w2 is equal to 0, 0. Turning this into a system of equations, we'll get w1 plus w2 equals 0, and 7 times w1 plus 7 times w2 equals 0. Got that nice redundancy in the equations there. So I'll pick perhaps w1 equals 1, w2 must therefore equal -1, and that gives us our next eigenvector, 1, -1. All right, so we have our eigenvectors. We have v and we have w. And since we also have our eigenvalues, we're ready to put these together and get a diagonalization. So let's go to the next page. And so recall for the diagonalization that D is the matrix with the eigenvalues on its diagonal. So lambda 0, 0 kappa. In this case, those values were 3, 0, 0, and -5. Then P was the matrix which has the eigenvectors as its columns. So v1, v2, w1, and w2. I need to remind myself of what those were, so let's go back a page. V was 1, 7, W was 1, -1. 1, 7, 1, -1. Once we know P, we also need to calculate P inverse. And so P inverse is, for a 2 by 2 matrix, 1 divided by the determinant, which in this case is -1 minus 7, -8 times, so I'm going to swap the diagonal entries, -1 and 1, and make the off diagonal entries both negative. And so this matrix becomes 1/8, 1/8, 7/8, and -1/8. All right, so we can write any matrix A as P times D times P inverse. Right? We can write A as 1, 1, 7, -1, and then D, 3, 0, 0, -5, and then P inverse, which is 1/8, 1/8, 7/8, 1/8. And as an added bonus, if we want a formula for a to the n, all we really need to do, as we've seen before, is raise those both to the nth power. So that's about it for diagonalization. If we wanted to test that this worked, if you wanted to do a check, for example, you could calculate, for instance, calculate a to the third by hand. So calculate this the normal way, as a times a times A. And then you could also, for instance, calculate it using the diagonalization. So check that this is also equal to P times D cubed times P inverse. Right? If all of this math is correct, then that should work out all right. And that is the diagonalization of a 2 by 2 matrix.